we have these we have these 700 by 315 rectangular beams. So what happens here? We have a rectangular beam. Now we have this rectangular beam. Now in this rectangular beam, we have 700 millimeters is depth. (350 millimeters is the width, and is simply supported. So if I redraw this, it is simply supported and length is 7 meters, or say 7,000 millimeters. That is given here. Residential building contain following reinforcement along the entire length: 2 N bars at the effective depth of 50 and 4 and 24 bar effective depth of this one. So they have give you 4 and 20 bars, and you have 2 bars here. So you have 4 and 24 bars, and you have 2 and 20 bars, and an effective depth of at effective depth of 50 and for an effective depth of 645. So that is 50 from here, and then 645. The top surface of the beam is not exposed to the atmosphere, so it is an interior beam. The beam is required to support following uniformly distributed load. So there is a 30 kilo, so there is a UDL load of 30 kilonewton dead load, and plus something 20 kilonewton. Of course, we need to account those short-term factors and live load factors. So that is the loading given to us. Now predict the following short-term deflections. At the level of load, what caused the cracking to initiate? So at what level? So it says that what level. So let me show you something. I think I have a quick explanation here. So so what happens here in the beam? So let's say you have these actual beams, right? The one that is you saw, and there is a, let's say, reinforcement given to here. Now when you load the beam, let's say you load the beam in the machines or somewhere. When you load the beam, your bending moment diagrams would be like this, right? So at some point, if you keep increasing the load, you will reach at one point your beam will start cracking. That moment is called cracking moment, like for examples here. So when your beam is here in this zone, you don't have any crack, but if you keep loading the beam, it will reach the cracking moment and your beam will crack. Now that you can see the beam has crack when moment, your applied moment is greater than the cracking moment. So in this zone you have a cracks. So basically it says that in the crack regions you can't take the full, because in these regions your concrete is not effective, concrete is cracked. So you can just say that okay, you have cracking moment of inertia and a gross moment of inertia. So that's what it says, that we just need to take, so I effective comes into the pictures to have combination of this gross and cracking moment, because you can see that here is the total, there is no crack, so you have gross moment of inertia. In here you have a cracking moment, because your this area is completely gone, right? Because it's cracked. Now that's what explaining it here, that you have this cracking load where the load will, so you keep increasing the load, you reach at this point, and then your beam will start cracking. You can see that. So if I draw this line, this is your gross moment of inertia. Gross moment of inertia is just like if you have rectangular, I equal to BD cubed over 12 plus AD square. That is just a gross moment of inertia. Yeah, I think in our lectures I explain you how you can calculate this gross moment of inertia. Gross meaning the full beam is effective. There is no crack, meaning that everything, the concrete will going to carry the moment. When crack happens after this point, they will crack. So you have this cracking moment of inertia. You can see this is significantly lower. So if it's crack, then you have these plastic neutral axis, and this portion is gone, right? You just have only this part, only this part. So in that case, you have cracking moment of inertia, which is significantly lower. But the standard saying that, look guys, if you have cracking, still, if you have this cracking, if you have this cracking, but in between the cracks, the concrete here, concrete here, concrete here, concrete here, concrete here, concrete here, still it can contribute some amount of resistance to the tensile moment, right? There is a tensile because it's not good in tension, so still it has some kind of resistance in the tensions between the, at the crack it will not have resistance, but the concrete between the two cracks has some resistance to the carry the tension. So therefore standards saying that, why don't you, because if you take I crack is too small, I gross is too high, then the standard saying that, okay, that's fine, you calculate I effective, that is the between I crack and I gross, right? So that's what the standards give you, that equations in the standards to calculate I effective. I effective basically, so this phenomena is called tension stiffening. Tension stiffening. Tension stiffening. So that basically this explaining this tension stiffening. So that's tension stiffening is representing these values. Now here you have this tension stiffening given to you considering this I effective. So basically our main goal is to calculate I effective, because we have equations. We have many equations. If you go to SD1, we have those equations in calculating deflections. All those parameters are known to us except this I. Because in SD1 we take into account I gross because it was just elastic region, we don't go on the cracking region. But here in the advanced subjects like SD3, we need to consider that beam is cracked, right? We can't just say that beam will not going to crack. So therefore we need to calculate I effective. If you long time ago, like if you consider the structure before 1950, 1930, they are massive structures, meaning that they design the structures in this zone, meaning that they don't want to crack the beam. So to consider those not to crack, they are massive members. If you consider the old structures, if you look at the old structure, heritage structure, those beams columns are made of larger cross sections. So they just use this I gross, right? They don't load the beam, so they generally have bending moment diagram like this, just under the I crack, right? They don't reach, they don't want to exit. So for that you need massive beam, right? Because to take into account this one, you need to have a massive beam. So those structures are very stiff. But with the research and all which now these days, so they said, okay, you keep loading your beam, there is no problems. The beam will not going to fall. It will crack. That is not a big issue. There is a crack will happen. Look, there is a secret between engineers. The engineers don't tell the users. We assume that the crack beam will crack. You see what I mean? We design it. In actual reality, the beam is cracked, right? You can't avoid the cracking. The cracking is completed. Completed that one. So that's what we are trying to do. That I effective in that zone. So and I effective just take into account. So here they say at what level load will cause the flexure cracking will initiate. So this one they want to know at what load that this is the starting point where the cracking will start. So they said what would be this load when the beam will. So you keep loading the beam 1 kilonewton, 2 kilonewton, 3 kilonewtons. You keep loading, keep loading, keep loading, keep loading. At one point, it will start cracking. It will start cracking, meaning it will have this crack happening. So that's the load that they wants to calculate. Under the short-term serviceability, this one you need to calculate I gross, calculate I crack, calculate I effective, and total long-term deflection delta total, concrete compressive strength given, the shrinkage strain is given to us. So now let's calculate these examples now. As I mentioned, so I'm planning to show you this one step by step, not just running over on this one. Let me open that examples here on my screen. So let's start solving these examples. I think you have all the details there. Our ultimate goal is to find these what we call I effective and I crack. So let's say I can show it to you here that we want to calculate this I effective. That's I effective. So deflections that you want to calculate, this is I effectives that you want to calculate. Now, if I have this deflection here, I can show it to you here. So this deflections here, deflection equal to 5 WL to the power 4 over 384 EC I effective. Basically this is normal equations, this is I, but then this is how its deflections equation is if you go to SD1 class. But then in our case, let's say short term deflections, let's write short term deflections equal to 5 short term loading to the power 4 384 concrete compressive young modulus of the concrete and I effective. That is the short term. Long term loading, long term deflections, we have 5 WL long term L to the power 4 384 EC I effective. So they don't change, just these WS and WL change. And then you need to calculate this KCS as well. So delta total equal to delta short term plus KCS times by delta long term. So what happens here? This one is representing the deflections when the load is applied onto your beam, and the same day when it goes onto the service, instantaneous deflections. These long terms, after 10 year, 20 year, 30 year, you have these long term deflections considering creep and shrinkage. This is creep and shrinkage factor. So because in long terms you need to have this creep and shrinkage factor. So let's calculate this short term first, then we calculate this KCS, and then we calculate a long term. So delta short term equal to, we have 5 WS L to the power 4 384 EC I effective, right? So let's calculate one by one. That short term loading WS, short term loading WS. So WS equal to, we have equations for that WS. Let me make sure that I go on the right track. I think we just need to go through this one by one because they wants to calculate a deflection at those levels. So let's hold on these ones because I quickly jump on these ones. I quickly jump on this last part. Where is it? I jump on here. Let's calculate this first one, A. Just hold on to that information. A, we need to calculate the cracking load. Cracking load WCR. Where is it? Here. That's we need to calculate. Now, if I want to calculate the WCR, we can calculate by using that equations again. That same equations. That delta deflection equal to this 5 WL to the power 4 384 EI. Now in that equations we can just find the deflections and we replace this one by W crack, right? That is the load that we need to find. Now let's find those W crack as well. So that is W crack. Now we have these moments that we're going to calculate these moments. So as I mentioned, when you want to know this one, there is a cracking moments respectively here. So let's calculate the cracking moment. Cracking moment M crack, because this is a cracking load. So for that cracking moments, we have equations to find these cracking moments. Where is the cracking moment equations? I can show it to you. Now the cracking moment equation is here. Z FCT dot F sigma CS P on AG. Now P is the force in tendons. We don't have pre-stress, so we take P equal to 0. So I copy that equations. M crack. Let's put the T here as the standards wants. FCT dot F dash minus sigma CS plus P on AG plus PE. Now this one gets 0, this one gets 0. Now, so finally you have Z FCT dot F dash minus sigma CS. That is the equation. So let's work out each parameter one by one. Now the Z is our I over Y T. So moment of inertia, we can just calculate moment of inertia. Let's say 700 by 350. So I, we can calculate first. I is equal to BD cubed over 12 AD square. So B is 350. Let's say about this axis, x axis coming from the centroid. So 350, which is parallel distance over perpendicular distance cubed over 12, area 350 times 700. D distance is 0 because the centroid of this whole section and the centroid of these whole sections are aligned on top of each other. So there is no distance D, so that is 0. So basically this will give you 1 times 10 to the power 10 millimeter power 4. Distance YT that you can just calculate by 350 by taking half, because this is the distance YT, right? If you remember that this is the folder 5, the top fiber or folders fiber from the centroidal axis, and that is 700 by 2, we have 350 millimeters. So in that case the Z equal to I on YT. I is 1 times 10 to the power 4 millimeter power 4 over 350 millimeters. So the first things we can calculate Z is 29 times 10 to the power 6 millimeter power 3. So that's Z we calculated. Now let's calculate this FCT dot F, which is a which is just your concrete tensile strength 0.6 FC dash. Now where you can find that? I can show you where you can find that. So if you go all the way to the this one here, which is the characteristic flexure tensile strength of concrete FCT dot F close 3.1.13 on page number 45, you have 0.6 square root FC dash. So 0.6 times square root 25, and square root 25 because you have these 25 megapascals given in your examples, which is concrete compressive strength. Now this value you get 3 megapascals. FCT dot F we found. Sigma CS, which we going to calculate sigma CS, where the equation for sigma CS, I can show it to you here. So if you come back to the close 8.5.3.1, sigma CS is equal to 2.5 PW minus 0.8 PCW 1 plus 50 PW EC sigma CS. So you have PW 0.8 PCW over 1 plus 50 PW ES ECS. Now so that is the equations. I just take it from close, and I show you where it is, right? Close 8.5.3.1. Now in that one, let's work out the values one by one. PW, just PW, if you come back here, just down below, that you have AST plus APT on BW on D. So I'm just copy that one. AST plus APT over BWD. Now here APT I think that's APT. I think they have not shown here, but I remember APT is the area of tendons. If you want to have that definitions, you can come back to the start of the standard, and APT cross section area of tendons, right? So we don't have tendons, like we don't have pre-stress, so we can just make it APT as a 0. So this part is 0. So basically we need to calculate AST over BWD. Now AST, area of the tension force, right? You have these 4 bars. How much was that? Was 4 and 24. 4 and 24. So AST equal to, if I go back and take the Rio table, uh, 4 and 24. So you have 4 bars, 24, 1808 is the AST value. So you have 1808 millimeter square. BW, this is your BW, which is 350 millimeters, and your D value is 645. If it is given here, right? 645 millimeters. So you have 645 millimeters. Sorry, 645 millimeters. So in that case, if you just take the ratio, you get 8 times 10 raised to 3 as a PW. So we found this PW. PCW, what is PCW? PCW is a wave reinforcement ratio of compression reinforcement. So we don't have any compression reinforcement in the wave, so we just take it this one 0. PCW equal to 0. And PW is there, Young modulus of the steel 200, ECS is given in our example. So let's calculate this sigma CS. Sigma CS, by the way, sigma CS is a shrinkage induced tensile strength, is a tensile stress due to shrinkage. You know, the concrete shrink, and those shrinkage will cause the tensile stress in this concrete. So 2.5 times PW was 8 times 10 raised to minus 3 PW over, this is get 0, 1 plus 50 times 8 times 10 raised to minus 3 times Young modulus of the Rio bar 200 EC, and this shrinkage strain is given in our examples. I can show it to you that 10 raised to minus 6. If you go back to the questions, it has this Young modulus 800 times 10 raised to minus 6. So if you just plug into the calculators, you will get 2.29 megapascals tensile strength of the tensile stress of the concrete due to the shrinkage. So we have passed a long journey so far. We have all Z calculated, FC taught that, F calculated, sigma C. So we are ready to calculate the cracking moment. Cracking moment equal to Z FCT dot F dash, take away sigma CS. Z value we calculated here, 29 times 10 to the power 6, 29 times 10 to the power 6 millimeter cube. FCT dot F we calculated 3 megapascals. 3 megapascals. Take away the shrinkage strength, we calculated 2.29 megapascals. So if you just simplify that, you will get the cracking moment of 20.4 kilonewton meters. Right. Now, once you know the cracking moments, we can calculate the cracking force, right? Because you have this UDL load. You have this UDL load is given to our examples. It says that the length of this beam is how much? Length of the beam is 7,000 millimeters. And we need to calculate this cracking load. How much cracking load that we needed. So we have this cracking moment. we have this cracking moment MCRT, and we need to calculate this. So you know this bending moment diagram, cracking moment or any moment, the maximum moment for this load is WL square on 8, right? The uniformly distributed load simply supported, that's the maximum moments in the simply supported beam UDL load. So M crack T is equal to W crack times L square on 8. Now this M crack T is this 20.4. Let's write it down here. 20.4 times by 1000 to convert into Newton. So we have this Newton millimeters equal to W crack. Length is 7000 square because it's given here over 8. So if you just simplify that, 20.4 times 1000 times 1000 times by 8 over 7000 square, you get W crack. So that is the first answers that you get. So W crack equal to 3.33 kilonewton per meter. So basically saying that when the beam will going to get 3.3 kilonewton per meter, your first crack will appear. So that's what the first answers we've done. The first answer is at what level the crack will appear. So that level, which is here 3.3 kilonewton per meter, when your load will at this load you will have a crack appear. Now let's say you want to calculate this deflection as well at A. So this is the cracking load, this is your cracking load, and then let's say what is your deflection at crack. So if I want to calculate these deflections, you know these equations, like if you have a UDL load on simply supported beam and it will deflect, if you want to calculate these maximum deflections, W5 WL to the power 4 over 384 EI. Someone said where this equation is coming from? Go all the way back to SD1 last year semester 1. You can find the lecture notes. We have all the derivations how we going to get that deflections. You don't need to remember that. I think in the exams you can just get it from the tables, or we can give you that one in the exam. So you have 5 WL4 over 384 EI. In this one 5, this is the cracking load because you have cracking load here, which would be your 3.33 kilonewton per meter times by the length is 7000 to the power 4 over 384. E is Young modulus of the concrete. Now if you want to know where is the Young modulus of the concrete for 25 megapascals, you can go all the way back to the table here, table 3.1.2, Young modulus of the concrete 25 megapascals, you have 26,700. So 26,700 because you have 25 megapascals coming from here, because you have given concrete compressive strength 25 megapascals. So from table 3.1.2, from table 3.1.2, you can get EC is equal to 26,700 megapascals for FC dash of 25 megapascals. So that's EC. And moment of inertia. Someone might say, what would be this moment of inertia? This is a gross moment of inertia, of course, because your beam has not cracked, right? Yeah, this is the point where the first crack will appear. So you can just use the gross moment of inertia. You don't need to use the cracking moment of inertia, or you don't need to use the I effective. So that's we calculated here. 1 times 10 to the power 10. So that is 1 times 10 to the power 10 millimeter power 4. So if you just simplify that, you get about 0.4 millimeters. So that is your A, right? So if I in this diagrams we calculated this one, which is 0.4 millimeters. We calculate 3.3 kilonewton per meter, which is your cracking load. We calculated 0.4 millimeters, that is the deflections here, when the first crack appears, right? So that is we calculated. So that's the whole procedure, saying at what levels of the load well the fluxes cracking will initiated. So that's the first point where your crack will initiated in this scenario. So, and you can see there is a I gross that we use. Now the second questions, we need to calculate I gross. Now to calculate the I gross, I think I gross we already calculated. If you remember that I gross, here you go. I gross is this one. So let me calculate, even let's just for report that one. B1 calculate IG, which is the gross moment of inertia, and that we calculated 1 times 10 to the power 3, 10 millimeter to power 4. Gross moment of inertia meaning that your whole cross section here 350 by 700, you have whole section is effective. There is no anything. So it's just calculated by taking I is equal to BD cubed over 12 plus AD square. Please note D distance is from the centroid of this whole cross section and centroid of those whole cross sections. So D distance is 0 here, D equal to 0. So this whole term is gone. B is 350, D is 700 cubed over 12. It gives you that gross moment of inertia. I just show it to you again. Now we can calculate this second. I think we calculated this load. We calculated I gross. Let's calculate I crack. Basically this one. I crack. That's they wants to calculate for us. So let's say B2. B2 crack moment of inertia, denoted by I crack. It is basically when the beam will going to crack. The beam crack meaning that it will just going to crack under these loading conditions, like when the beam will loaded here. Now we are here in this. So did I draw the diagrams? No, I did not draw the diagrams. So probably I can draw it up again. So it's basically saying that you have this beam. Now you are loading your beam more than crack load. So your beam will going to crack. Your beam will have this crack. Let's say this one here. And if I draw the bending moment diagram, so in this zone, which is your M crack, in here M crack, more value in this zone, in this one, you have this crack appearing in this zone. So for that one, they said calculate I crack, right? Moment of inertia. So now to calculate I crack, let me draw the diagrams first. So you have this bar, which is 4 and 20. 4 and 24, I believe. Let me check. It has these 4 and 24 and 2 and 20. So, and then you have these 2 and 20. And let's say this is 2 and 20. You have this 350. You have this 700. Now, to do this one, we have this axis. This is called plastic neutral axis. Plastic neutral axis meaning that your beam will going to have broken because the concrete below this plastic neutral axis will gone. So for that, let me draw up the concrete which is above this axis, which is a compression zone. And for this compression zone, concrete will be active. Concrete will be active meaning that it will have resistance to the bending moments, 350 millimeters. And this line, which I represented by dn, which is, let's say, depth of the neutral axis, right? We don't know this depth. We just want to find that depth. But this is the plastic neutral axis. I will tell you what is the meaning of plastic neutral axis, because basically your beam in this region, it will plastically deform. It will not going to go back into the original position. Before Here I gross and all. When you release the load, your beam will going to go because this is still in the elastic zone. But here now, like here you have this elastic zones where your beam going to recover. Now we are working on here, right? It's going to crack. So in that case, we have not working with the elastic neutral axis. Like here we have elastic neutral axis. Elastic means it's going to go from the CG, centroid of the cross section. That is the elastic neutral axis, ENA. So which is going to the centroid of the axis. It is symmetric, so it is very easy to find the centroid. Otherwise, you can calculate this centroid by if you remember that centroidal axis equal to A1 Y1 A1 Y1 plus A2 Y2 plus A1 plus A2 and so on. So you have this centroid, but here is a symmetric. We just take it half. Now this is plastic neutral axis. This is PL plastic neutral axis, PNA plastic neutral axis. This is PNA, not ENA. So for plastic neutral axis, our concrete will be cracked below this neutral axis, and the concrete will not going to consider as an effective concrete. Now we have a simple assumption saying that we can't work with two materials when in the plastic zone. We can't have concrete and steel and then we apply this equation. No, these equations are pretty standards meaning they will work for only one material. So we have steel and concrete sitting together, so we need to convert. Basically you have options meaning you can either convert steel to concrete or concrete to steels, because concrete is the big chunk materials here, so we just convert your steel into the concrete. So what happens here? So let's say below this axis you don't have any concrete, so that's why let me put, let's say this one here, let me put the chunk of concrete instead of steels. So this 4 and 24 bars, there is a steels, but then I like to convert this steel 4 and 24. What was the area again? Area of this steel bar AST was 1808 millimeter square. Now we need to calculate the equivalent area of the concrete. Let's say area of the concrete in tension. How much area of the concrete that we can put in instead of steels? Someone might say you can put 1808 millimeter square, same amount of concrete you can put it there to replace the steel. No, it is not possible. Why? Because the Young modulus of the steel is 200,000 megapascals and Young modulus of the concrete is how much we calculated. Let me go back and check it. Basically we can just get it from the tables rather than looking into that. So Young modulus of the concrete, we have 26,700. So we have 26,700. So we have this gap because different Young modulus, you can't have different same concrete area. So that's why we calculate the modular ratio. Modular ratio denoted by n, small n, and this modular ratio is the two materials has a Young modulus. So take the big Young modulus over low Young modulus of the materials. That's how you calculate the modular ratio. And let's say this 200 megapascals over 26,700 megapascals. So the modular ratio that you're going to get here is 7.5. Right? There is no unit for that. So now it's okay to do the calculations. Calculations mean your AST equal to 1808 millimeter square. So if you want to calculate the equivalent concrete in tension of this force, you can have just multiply this n with the 1808 millimeter square. So you have 7.5 times 1808 millimeter square. You will get 13560 millimeter square. So in that case, you can have this area of the area of this part here. Let's say NAST equal to, we just calculate it. Let's calculate it again here. 1808 equal to 13560 millimeter square. Now here we have these steel bars 13560 millimeter square. Now we can just replace this bar here as well, the top one, which is under the compression. Now here there is a one challenge, that when you remove this bar here, they will have holes, meaning when you remove this bar, you need to fill those holes as well. Now to fill that holes, we have n-1 AST. So basically you just need to add this. Basically this is an AST, take away AST, right? So you just need to add this V minus because we just added that one, and if you bring it other side, you need to take it away. So that's the simplification of n-1 AST. So basically this becomes 6.5 times 18. I think this area we have different area, which is 2n20. So let's get that 2n20. 2 and 20, which is 628, which is 628 equal to, you will get 4082 millimeters square. So we have everything concrete now. That everything concrete meaning you have this steel converted into concrete, and those steel are also converted into concrete, and this position is 50 from here. This position is 50. So this distance would be dn take away 50. This one we have 645 or something. Let me check. How much was that? 645. Yep. So we have these. We have these 645 millimeters. So that 645 millimeters is notified here. Now we can calculate this from here to here. 645 take away dn. Now, so we have all this one. Now our main goal is to calculate this dn, where the neutral axis is going to act. Above the neutral axis you have compression, below the neutral axis you have tensions. Now there is a we can take the first moment of area. So first moment of area meaning that below the neutral axis and above the neutral axis you have equal area. That's what this first moment of area that's represented, that value. So it is like this. How many area we have? Area number 1, area number 2, and area number 3. There are 3 zones. Okay, so let's work out the first one. Let's say A1 Y1 plus A2 Y2 equal to A3 Y3. Okay, because above the neutral axis there are 2 zones. Zone 1, zone 2 basically is concrete, and these steel bars, this is zone number 2, and this zone number 3. Area of the one, which is basically 350 times dn. So easy, 350 times dn, that is area. Distance from centroid to the neutral axis is dn minus 50. Just give me a minute. Dn minus 50. No, this one here, sorry, this one. So it would be your dn divided by 2. So you have this dn divided by 2 plus second zone is this area is 400,082. I think there are 82 here. So 4082 millimeter square times by this distance is dn minus 50 is equal to area 3 is 13560 times by 645 minus dn, right? So that's the whole scenario, a1 y1, a2 y2, a3 y3. I hope you understand that. Now this is quadratic equation, so it's little bit challenging, but it's doable. So you just simplify that. 350 over 2 is 175 dn square, plus you can just have a 4082 dn minus this multiply by 50, you get 24100 equal to, you can expand this bracket as well, 8746,200, take away 13560 dn. Collect all the like terms here, 175 dn square plus 17642 dn, bring those across to equal to sign, and then you have 8950,300 equal to 0. So I just bring this one across and multiply or minus respectively. Now you know this equation, let's say ax square plus bx plus c equal to 0, where you can have a equal to 175, b equal to 176.42, c equal to minus 8950,300. In that one, you have, let's say, if you want to calculate dn or x, dn equal to, you have this equation minus b plus or minus, you know these quadratic equations, right? The solution of the quadratic equations. You can just plug the value, minus 176.42 plus or minus 176.42 minus 4 times 175 times by 8950,300 over 2 times 175. So I just plug the values that you see on the screen. And then if you just simplify that further, you will get something like minus 17642 plus or minus 95.31 over 350. So you can just do two scenario, minus 17642 plus 81095.31 over 350, or you have 17642 minus 81095.31 over 350. Now one numbers will going to make sense, another one will not make sense, meaning that with this plus sign you have 181 millimeters, or you have another one which is minus 282 millimeters. And in that case, we can just cross this one out, this 181. Always you check whether those numbers making sense or not, because look, 181 millimeters, so you have about 700 millimeters, so 181 millimeters dn makes sense, right? So that's 181 millimeters makes sense, so that's the dn. Now we need to calculate the moment of inertia for those parts. So moment of inertia, there are three zones meaning you have concrete 1, concrete 2 and concrete 3. For those concrete 1, we can just calculate the moment of inertia for the hole, that will be your I crack. So your I crack equal to I1 plus I2 plus I3, right? So that is the moment of inertia for those three zones, as you can see there. First you calculate this neutral axis, we can calculate those three zone moment of inertia. Now let's get this, let's make the table. You have shape. Let's first get this concrete, number one concrete. In that concrete, let's say the equations would be I1 equal to I0, let's put I0 plus AD square, right? So let's say we just get I0 is just BD, let's put millimeter power 4, BD cubed over 12. So basically you have this block, you have this 350, dn is 181, so you have 350b, d is 181 cubed over 12, so you get about some big numbers there, let me get that big numbers. 350 times 181 cubed over 12, you get 172,950,779.2. Let's draw the line, and I0, then after you have area, let's say area millimeter square 350 times 181, so you get 63,350. Then you have D millimeters. D is this distance from the centroid, this one dn divided by 2, so that is the D from centroid to the neutral axis. So 181 divided by 2, you get 90.5 millimeters. So we calculate everything. Now in that case, you can just I0 plus AD square, which is this number, plus this number times this per square, this one. So it's basically 172,950,779.2 plus 63,350 times by 90.5 square. You get about big number 691,803,116.7. All right. So any questions so far? I'm just keep talking. We done this first one, which is this concrete one. Let's do the second part, which is the concrete in compression. This compression state or concrete in compression. So let's say second shape, compression steel. Let's say it's not steel, it's concrete, but let's represent as a steel. Look there. The area is very small, the BD cubed over 12, so we just not taking it into account compared to this concrete one, so we take it 0. Now area we know, we consider that area 4082. Let's put that 4082 millimeter square, and D is the distance here. Where is that? dn minus 50. So you have how much dn? 181 minus 50. 181 minus 50, you get 131. And for that case, you can have 0 plus area is 4082 times by dn is 131 square. Please note, in the exams you may not need to perform all these calculations. This is your mechanics of solid all the way to first year, but to completeness of these examples, I'm just showing you the whole things. But in the exam, sometimes they will give you eye gross, sometimes they give you eye crack, sometimes they give you cracking moment, or sometimes they give you applied moment. So you just need to look which value has given to you and go through it. So you don't need, so prepare yourself. It's not like you said it is open book. I will just do it on the day of the test, and I will just look at the solution, and I will just going to absorb everything in 1 hour. Well, if you open the solution on the, my strategy is open book exams is quite sometimes time consuming, because you're going to open the solution, try to understand on that day, and then half an hour gone. So it's not a good strategy. You need to make it sure that open book just to extract those information. Just get that area, and the distance is 645, take away dn. 645 take away dn would be 181. You get 464, and then you have, let's say, 0 plus 13560 times by 464 square. You get about 291,941,3760. So if you just sum this all up, this one plus this one plus this one, you get 3681 times 10 raised to 6, which is your eye crack, millimeter power 4. Right, so that's your answer for this second one. This answers for this second one, meaning here you go.
I gross we calculated, I crack we just found it. Okay, so that's I crack we found here. We found this I crack. We found this I gross as well. Okay, so look at this. I effective should be in between this I gross and I crack. Okay, it will not be something different. So once you calculate the I crack, we can calculate the deflection at, we can calculate B, this one, B2, right? That deflections when the beam is fully cracked. That was the value that we use. So let's say we want to calculate this B12, B2 deflections, because you remember this B1 which is 0.4 millimeters. So B2, what was that? B2, right? B11 we did not calculate B11. I think I gross. Okay, we can calculate B11 first because we have somewhere I gross. Let me, oh, here you go. Let's put some space here. Let's put some space here and let's calculate this. Is it right way? Is it doing it? Yeah, it's doing it, but wrong way. Okay, let's do. Yep, let's do it properly. Okay, there you go. So we just want to calculate this number. This I missed that one. This B1, I think the deflections. Let me check my calculation. Yep. So let's say B1 deflections. We can use the same equations. B1 deflections. It is basically deflections due to the I gross. So you have 5 loading length 384 EC I gross, right? Because we want to calculate an I gross. 5 times 44. We calculate the short term loading, I believe. We did not calculate the short term loading. We can calculate the short term loading first. Here is short term loading. Short term loading would be 30, 20, science 0.7. So short term loading first we calculated. Sorry. Let's do the short term loading, that G dead load plus short term factors times live load. This was how much? This was 30 and 20. You have this G is 30, G is 30, Q is 20, and this is short term factor. So you have this 30 plus 0.7 times 20. Now someone might say, where you get these equations? Now if I take you all the way back to SD2 last year, you may remember that for serviceability you have this G plus short term load factors times by Q. Now someone may say, why you not multiplying these short term factors with dead load? Because the dead load on the day one, when you open your buildings or for service, your dead load is there, but service load is reduced by 30% and so on. You can see there are 30% reduction in the short term. It means that, look, when you open your buildings on the day one, you may not get all the users that you are predicted for. Like on the day ones, the building will not going to have those 20 people that you are predicted for, meaning that you may not get those 20 people on the day 1 minute first minute, right? You might have some inspection or something else, right? Some guest and all, but you may not have it. So you can have 30% reduction. So therefore it just multiplied 0.7 and 44 kilonewton per meters. So you have 44, length is 7,000 millimeters square over 384. EC we got it 26,700, and I gross is this 1 times 10 to the power 10. So in that case you have 5.2 millimeters. So that's good. We calculated 5.2 millimeters. Come back here, you have this 5.2 millimeters. Now we can calculate this B22. B22 deflections due to eye crack. So the same equations that we can use it just to change this eye gross to eye crack. So deflections at B22 is equal to 5 W short term loading L to the power 4 384 Young modulus of the concrete and eye crack. So 544 we calculated, length is 774. Someone might say you use kilonewton per meter, but because you have these times by 1000 to convert into newton, divide by 1000 to convert into millimeters is cancel out, so you have 44 newton per millimeters. 384 times 26,700 megapascals newton per millimeter square times by eye crack, we just get it 3681 times 10 raised to 6 millimeter to power 4. So eye crack you have 14 millimeters. Keep an eye on those numbers, right? It's making sense. Look at those numbers. It's making sense that you have these 14 millimeters. You have these 14 millimeters B22. Now, so you have 0.4 when the first crack will appear. This 5.2 is at the service short-term loading when your gross moments will be there. So there is probably not anything like due to the gross moments. Now here your beam is fully cracked, 14 millimeters. Look at that, is very huge. Now B3 that we're going to calculate, that is based on I effectives. Let's do the I effective now. Because we need to calculate this I effective now here, third one. So let's do the I effective third one. B333 I effective. Now you remember this I effective because you have this tension stiffening, and due to this tension stiffenings we have this I effective. Now this I effective, where I'm going to get it, oops, just on the section 8, and there is the equations here in clause 8.5.3.1. you have these equations I effectives. So let's copy that equation. I crack 1 minus 1 I crack over I gross. Basically this is I gross, okay, the I itself, M crack T over MS star, okay, and there is conditions that you need to check with I effective maximum. It should be I effective maximum less than, so that we're going to make a check. Now let's say I crack. What was the I crack? In that ones we have everything. We need to calculate this MS short term, this deflection due to the short term loading. So let's say MS star, which is the applied moment, basically this applied moment. Let me redraw the pictures here. Basically it says that you have this loading which is short term loading. You know that WS is equal to 44 kilonewton per meters, basically G plus psi S Q. That's we calculated, and because of this one you have this moment which is applied moment MS star. For this one you have WL square over 8, WL square over 8, you have 44 times by 7,000 square over 8 over 8 over 8. So that you get is 270 kilonewton meters. So we have all the values now. I crack, we calculated I crack was 3681. 3681 times 10 raised to 6 millimeter to the power 4. 1 minus 1 minus I crack is 3681 times 10 raised to 6. I gross is 1 times 10 to the power 10. Cracking moments, MCRT. I think we calculated the cracking moment before. Let's get that cracking moment from somewhere. Cracking moment. Yep, W. I think there was a cracking moment inertia. Where did we calculate those IS and all? Oh, here you go. Cracking moment is 20.4 kilonewton meters. So it's kilonewton per meter. So we no need to convert into Newton millimeters and so on. So that is cracking moment 20.4, and MS star we just calculated 270 kilonewton meters. Right? So if you just simplify that, you get 3694 times 10 raised to 10 raised to 6. There are a couple of checks we need to make. Millimeter to power 4. Now check number 1. First checks we're going to make. Check number 1 is what we calculated I effective should be I effective maximum. Now I effective we have 3694 times 10 raised to 6 millimeter power 4, and this is basically your gross moment of inertia. Is basically 1 times 10 raised to power 10 millimeter power 4. To make a meaningful comparison, we can just make it into 10 to the power 6. 1 2 3 times 10 to the power 6 millimeter power 4. So you can see this can be cancelled on this side. So 3000. What happens here? Oh, okay. So you need to have one more zeros there. Times 10 raised to, is it right? 1 2 3 4 5 10 raised to 6. So let me check. 1 times 10 to the power 10, take away 3694 times 10 to the power 6. Yes, so that is right. So 1 times 10 to the power 10, you get let's make this comparison. So that's looks okay because this value is bigger. If I just want to convert 3694 times 10 to the power 6, 3694 times 10 to the power 6 times by 3. So that's the values. All right, so that is okay. I think I check in my calculator that this value is less than this 1 to the power 10 to the power 6. So the first check is okay. Now there is a second check that we also need to make it. That second check I can show it to you. That first checks that we need to I effective maximum. Basically it says that this value that you are taking it should follow this this value. That basically saying that this value it should be less than this one. Your graph will not have like this. It will not gonna follow like this. Otherwise you will have this I effective, right? So it will not gonna happen, right, in the reality. So therefore they want to make sure that this graph, this value that you predicted is less than this one. So that makes sense, right? So that is okay. Check number 2. Check number 2 is okay here. Now check number 2, you have maximum effective second order is taken as I. So this is gross moment of inertia, that's we done. for reinforcement section when your reinforcement ratio should be greater than or equal to 0.05. So we just calculate this one. P equal to AST on BD. Your AST would be 1808. If you remember that we calculated AST 1808 millimeter square. I can show it to you again. 1808 millimeter square, because you have 4 and 20 bars. In the tension zone you have 4 and 24 bar, you have 1808. So for that 1808, so you have 1808 millimeter square over BD. So you have these values here, 350 in 4 bar, and here is 645. So you have 350 times 645 millimeter square. 640, by the way, given in our examples. So if you go back here, you have 645 millimeters depth is given to you. So you have 1808 over 350. So if you just calculate that reinforcement ratio, you get 0.008. So P, which is reinforcement ratio, 0.08 is greater than 0.005. Therefore, it is okay. So therefore, it is okay here. Look, you need to make these checks to making sure that this equation is valid. If it's not, then you need to do this. If it is less than 0, you need to take this I effective maximum as a 0.6 I, and you need to redo calculations. Therefore, it is very important that making sure that you are using this I is valid for these two conditions. Otherwise in the test, if you don't do these checks, you can't say that this answer is okay, because then you need to have to use 0.6 I. Okay, so for that case, please make sure that you do these two checks. Very important that if you don't do the checks, you're not validating your answers. Now we done all these calculations. I think we did not calculate so far B3. Let's calculate B3 now. Deflections due to B3, make sure I don't forget that. So B333 deflections due to I effective, delta B333 5WL to the power 4 over 384 EC I effective. So 544 7000 to the power 4, 384 26700 times by I effective is we validate that answers 3694 times 10 raised to 6. So if you simplify that, you will get 14 millimeters. So let's plug that here. You have these is almost same, 14 millimeters. Why is that same? I think it's almost very close to I crack, so 3681, because you can see the difference is here. 110. If you just use the decimal place, there are minor difference, but it's very close. So you have 3681 cracking moment of inertia, and this one here you use this 3694, very close to each other. So therefore, if you put the decimal places, that will you can see some difference. So that's the deflections B3. Now we need to calculate the total deflections, because the last question is to calculate total deflections, right? Last question is to calculate the long-term deflections, total deflections. So basically total deflections is the deflection. Let me explain you that. delta total equal to delta short terms loading. If you remember that on the when you buildings goes on the service on the day 1 first seconds of the service day, what would be the deflections, that is delta x, plus let's say someone asks you after 20 years 30 years what would be your deflections um, due to the long-term sustained loading. So that is the deflections due to the sustained loading. Why you multiply this one? Because you have creep and shrinkage in the long term, creep and shrinkage factor. So you need to multiply that factors. These factors might be reduce or increase your deflections depending on the situations, depending on how your reinforcements are organized, like how your reinforcement would be putting it together. So short term deflections we calculated. Where is the short term deflections that we calculated? I think short term deflection is this 14 millimeters. Please note this is the I effectives. You don't need to calculate because there are a lot of deflections that you have taken, right? Someone might say you have obtained a lot of deflections, like you use 0.04, you use 5.2, you have 14 millimeters, you have 14 millimeters here. Which one I should use for the short term? Look, this is a real one. This is a real one, meaning this is the when you do the laboratory test, this is going to happen. This is going to happen. So meaning that this is the real one. Real one means this is the one that you're going to use it. This is I gross. I gross meaning if you want to design for elastic, that is called working stress methods. If you long time ago, if you have 1930 or 1950 structures, they have this I gross, so they use 0.4, very small deflections. You see, when you have bigger cross sections and so on. So we don't use that. This is full. This is completely crack, not considering the tension stiffening effect. You remember that when your beam is going to crack, then you say that okay, don't worry about this region. That's what happens here, I crack. Well, in the reality it's not correct, right? Because in reality your beam will going to crack. We know in reality your beam will going to crack, but the region between this crack, the concrete between this crack will have a tension resistance, that is called tension stiffening. So for that reasons you have some resistance, the moment of inertia in these regions as well. Of course in the crack it will not going to carry any tension load, but the concrete between the cracks will have some effect, so therefore you have some resistance. So therefore standard saying you take I effective. For that case we use these deflections, right? So that is the short term deflections that we take into account. There is a Branson's, I think Branson. I think in the lecture notes you can find that author's name. He also have that kind of equations that you have it here, but it's kind of conservative. So I think in these new versions after 1965 he come up with that one. So over old standards 1980, 1970 they use Branson formula, but now these 2009 and these versions we use this latest formula that is coming from the research. I think we use this one from American or European. The American code and European code, they use exactly the same equations. I think I need to check which one is that, but they use exactly the same equations. We adopted from them, and we also done some research to validate that. So in University of New South Wales, we done some beam testings to validate these these equations for Australian practice. So I think it is quite validated one. As I mentioned, a lot of research has been done, and then we come up with this I effective one. So so therefore we take 14 millimeters here, 14 millimeters. I hope you understand that. Now let's talk about KCS. Now KCS has this creep and shrinkage. If you turn the page over, you have these equations, basically 2 minus 1.2 ASC over AST. You can make this one ASC, if it is equal, then you have 0.8. You can see if you put the equal concrete compressive stress strain, then you will have this equal to 0.8. You can reduce the deflections significantly. Some stars. So if you have, let me write that equations here, 2 minus 1.2 ASC on AST. Of course, there is a one check that we need to make it. So basically, when you have, look, this is the engineers wants to use this smaller value, smart engineers, that they try to play with something, then they need how you can make it smaller value. If you have this area and this area like ASC equal to AST, you can have these both equal, then or you can then you have 2 minus 1.2 times 1, you have 0.8, right? The standard saying that this is 0.8. Look at that, you can't go more than 0.8. So there is 0.8. That's how it says that you have this equal area, then you have 0.8, which is good. We are happy because you have smaller deflection in the long term. But we have this ductility and all these ones, so we have these equations where we have 2 and 20 bars and 2 and 20, 4 and 24 bars. So here you have ASC 2 and 20 bars, 628. Let me check I'm going on right track. Yep, 628. So 628 millimeter square, and AST equal to 4 and 24, 1808. 1808 millimeter square. So it's not 1 here in our case. Look, this is a penalty, okay? Penalty means standards we're just going to apply this 628 millimeter square over 1808 millimeter square. So 2 take away 1.2, so you will get about 1.6. 1.6. Now we need to make this third check number 3, because remember there are 2 checks we already make it. Check number 1, check number 2. Third checks we need to make is KCS is less than 0.8 or not. So KCS equal to 1.6, so it's less than 0.8, therefore it's okay. Where this one is basically this one. The standard don't want you to go less than 0.8. If it is less than 0.8, you need to use 0.8. So we calculate KCS, we can calculate this delta sustain due to the sustain load is a long-term load is equal to same equations we use, but here we have long-term loading. L to the power 4, 384 EC, and here we're going to use I effective basically because I effective is the real one. And here we use long-term load instead of, do you remember we use 44? We don't use 44 because 44 is the load when the buildings will going to open for the service on the day 1, right? That is the 44. You remember that 44 we calculated? Where did we calculate those 44? Somewhere we calculated. Here you go. The 44 we calculated. That is the day 1 G plus IS plus Q. So that is the day 1 when we open our buildings. Now long term, after 20-30 years, we need to calculate a long term load. So the long term load equal to, this is sustained load or long term loading. Now long term loading, your dead load does so standard saying that, let me open the standards. I think I misread that one. So standard said it should be greater than or equal to 0.8. So let me correct that. So it should be other way around. So the check is should be greater, right? Like that. Like that, right? So KCS should be greater than 0.8, right? So in that case, we have 1.6 greater than 0.8. So therefore it's okay, right? Does it answer the questions? Yeah. So sorry about that. It's just I quickly run over and I did not check the sign less than. So it should be greater, and that is given in the standard. So it is greater now. So it is okay. So here dead load does not change in the long terms, but the live load change it. So you have psi L times live load. So basically where these equations come from, if you go back to the SD2, we use these standards at that time, and the serviceability in G plus psi L long-term load times by the Q, and psi L long-term load is 0.4 given here, so that is the long-term factors. That is basically your long-term factors. Now, but in our questions, they have given you this psi L value that we're going to straight away use it. But that is for your knowledge where the value extracted. So psi L is given. So let's plug that value. So dead load is 30, I believe, kilonewton per meter, and then you have 0.4 times by 20 kilonewton per meter. You will get 38 kilonewton per meter, which is the long-term loading. So now we can plug all the values here. So delta sustain equal to 5, long-term load 38 kilonewton per meter times by L, which is 7,000 to the power 4 over 384 26,700 times by I effective 3694 times 10 raised to 6 millimeter to power 4. Now in that case you can get delta sustain is 12 millimeters. Now we have all the values that delta total deflection, short-term loading on the day one when you open the building, creep and shrinkage happens for long term, and then you have this delta sustain due to the long-term loading. So short-term loading 14 millimeters we calculated. KCS we calculated should be greater than 0.8, check. So you have 1.6 times by delta sustain is 12 millimeters. So in that case we will have 33 millimeters. Now the last checks that we need to make, this is check number 3. Now check number 4. Check number 4, that your delta total should be your delta total should be less than delta limit. Delta limit meaning the standards will give you that your beam should not deflect for certain values. So where you gonna get that delta limit? So if you go to AS3600 and then you have this limit for calculated vertical deflection of the beam and slab, all members, total deflection span over 250. So that is your delta limit. So you have span over 250, span is 7,000 millimeters over 250. You will get this 28 millimeters. So your delta total, which is 33 millimeters, is greater than delta limit. So 28 millimeters, therefore is not okay. The deflection check, service check does not pass. You need to redesign your beam. So so that is the check number 4, that your delta limit should be greater than delta total should be greater. So it says that the standard saying if your beam deflect by 28 millimeters, we are okay. But if it is more than 28 millimeters, your user will not feel comfortable and use your beam is deflecting too much, greater than 28 millimeters. Therefore, you need to do these recalculations. Now. There is a second methods as well. I can show you that second methods that we have equations that given in our lecture notes, and they will give you exactly the same values that you use. So there is a second methods that this equation L square on 96 EC. This is generalized equation, by the way. It can be applied to your simply supported beam, continuous beam, left side moment at midspan, moment at right. Right. So this is a very generalized equation. It can be applied for any continuous beam and simply supported beam. So let's substitute all these values here. Let me explain you this. I think everything was clear to you except this ML and MM. So you have this moment, bending moment diagram. So this is mm, this is the left side of the moment support, this is right side of the moment. In this one you can have wl square over 8 that you can just calculate. Let's say short term loading 44, you have 7 meter square over 8, you get 270 kilonewton meters, and those are zeros. So if you want to calculate this deflection using these values, you can calculate these using those equations. So let's say you want to calculate the first one, short term deflection initial one. So let's say you want to calculate the short term one. So 7,000 square over 96 EC 26,700 times by I effective average, which is 3694 times 10 raised to 6. You remember we calculate I effective. Left side moment is 0. The mid one is 270 times 1000 times 1000 to convert into Newton millimeter, plus right side moment is 0. Right? These are getting 0. So if you substitute that value, you get 14 millimeters. Right? This is exactly the same that we calculated using, I think, the previous methods. You have, yeah, this 14 millimeters that we calculated. So it's exactly the same thing. If in the exams, if you come across these kind of equations, don't hesitate to use it, or you can use that another one as well. Now if you want to calculate due to the sustained loading, let's say sustained loading, you remember this short term loading, we just calculated this lambda s. Basically I'm just showing you again this delta total equal to delta s plus kcs times delta sustain. So this is delta s. Now if you want to calculate delta sustain, which is basically again L square 96 EC I effective M left side 10 mm plus mr. Now in that case we can just calculate this delta sustain. Now again you have this mm, which is your long-term load now, because you have 44. Do you remember we calculated long-term loading? Long-term loading we calculated here 38 kilonewton meters. So if you just want to calculate 38 times 7 square over 8, you get this middle one 233 kilonewton meters. So length 7 square 96 26,700, I effective 3694 times 10 raised to 6. Some of the value now I remember by myself. Left side is 0. In the middle you have 233 times by 1000 to convert into Newton times by 1000 to convert into the millimeter, plus mr equal to 0. So if you calculate that one, you get 12 millimeters. Again it is same as we done this 12 millimeters sustain. And KCS is exactly the same. There is no any issue. So you have this delta total equal to delta short plus KCS times delta sustained loading. You have 14 millimeter, KCS we calculated 1.6, and you have 12 millimeters. So it is 33 millimeters, and delta limit we have 7,000 over 250 is equal to 28 millimeter. Since delta total, which is 33 millimeters, is greater than delta limit 28 millimeter, it is not okay. Right? So that's the few things that I just applied here. Review, just we need to have this calculate I effective. For that you can calculate m crack t, you can calculate I gross, you can calculate I cracked, and you can calculate ms. That is 4 values that you need to calculate I effective. Once you know the I effective, delta is just equations that you used for deflections. and then you do couple of checks that I effective is less than I effective maximum, basically is the gross one, I gross. Then you also check this reinforcement ratio is greater than 0.005, so that is check number 2. Check number 3, KCS should be greater than 0.8, and then third checks you can make delta total should be less than delta limit, and generally speaking delta limit is L over 250, right? So these are 4 checks, and generally this I effective is the challenging one, but you have these 4 different. Sometimes in the exams you might have given this one and you might need to calculate this. Sometimes it given to you, you might need to calculate this one given to you, and also you just need to use 1 or 2 to calculate this I effective, and then of course these checks need to be performed for your calculations. So that is the